Let's look at molecular structure and bonding. This is kind of the middle section of our class here. And let's talk about some of these questions here in the middle. So things like question number 20. Which molecule has exactly 2 unshared lone pairs of electrons on the central atom? Now, to do that, you're going to have to be able to draw. So this goes back to a concept that we went through very, very, very thoroughly right around midterm time. The correct answer is B, OF2. Now, as I was getting to, there are 2 approaches to this problem. We can either draw everything, and if we drew everything, we'd end up with these 4 structures minus the electrons on the outer fluorines. And you would have come to OF2 is the correct answer that way. Now, for your consideration here, let me present an alternative way of doing this that doesn't actually require us to draw. Because while drawing is helpful here, the whole reason I could get to those drawings so fast is because I didn't go through the process of calculating how many valence electrons were there, and then going through the process of drawing everything, putting all the dots in, making sure I had the correct structure, all of that stuff. How can I come up with B a little bit faster? Well, it does come down to, we do need to know the total number of valence electrons. So in the case of boron trifluoride, we had 3 plus 21 for fluorine, that's 24. For oxygen, we have 6 plus the 14 is 20. 5 plus 21 is 26. 8 plus 14 is 22. So we did have to do that part. We do have to calculate the total number of valence electrons. Questions like this usually pick on halogens because halogens are relatively easy. They have 7 valence electrons, and so they need to make 1 bond to get them to 8, which is their octet, which makes their calculation also very easy. I know that each one of those fluorines is going to pick up 8 electrons in total, 2 in the bond and 6 in the lone pairs. So if I subtract out, I need 3 groups of 8 for the fluorines here. That's 24. There are no electrons left over for the boron. 2 groups of 8 for the oxygen difluoride. There are 4 electrons left over for the oxygen. 3 groups of 8 on the nitrogen, leave 2 for the nitrogen. 2 groups of 8, 22 minus 16, 6 electrons left on the xenon. Divide each of those by 2. I'd have 2 lone pairs, 1 lone pair, 3 lone pairs. So this is a trick that we can use consistently through this particular section of the exam. Because when we have to draw multiple things, usually what we're going to look for are little tricks to make us so that we don't have to draw as much. And this kind of application where we can quickly determine how many electrons are on the middle atom, how many lone pairs there are, can solve for us a lot of things. Keep in mind, even though the ACS publishes a set table of constants, and that's supposed to be all that you get for the exam, we are not doing that. You are going to get your normal equation sheet. The one side is going to be all of the equations that we've used throughout the semester. It's going to be that equation sheet you've gotten for every single quiz, every single test, all semester. The other side is going to be those hybridization tables that we used on the Chapter 5 quiz and for exam 2. If you remember something about that particular hybridization table, if you could break the molecule down into bonding pairs and lone pairs, it immediately gave you hybridization. It immediately gave you shape. And so this kind of trick here can help you with that stuff as well, because you can look at this and say, okay, xenon difluoride had 2 bonding pairs for the fluorine, 3 lone pairs around it. That's a steric number of 5, 3 lone pairs, that's a linear shape. Bonding was 180 degrees. So you can draw a lot of information off of just this little bit here if you use your tables correctly, if you use them appropriately. So again, B was the correct answer there. All right, for number 21, consider the Lewis structure for CH3Cl. What is the best description of its molecular shape? Well, this one's probably best suited for drawing. I've got carbon in the middle. I'm going to have 3 hydrogens. I'm going to have a chlorine. Total 4 plus 3 plus 7 is 14. 2, 4, 6, 8, 10, 12. 14. So I've got the correct structure here. What I need to evaluate, and this is again where your tables come in, I've got 4 bonding groups, no lone pairs. So my steric number is 4. Steric number 4 with 4 bonding groups would be tetrahedral. Yes. Yes. So you will be given a double-sided, equation sheet. Equations on the one side, hybridization table on the other. So again, like I said, the real important thing here is if you can draw the shape correctly, or if you can do what I just did with the kind of the mathematical approach, you can very quickly determine a lot of things about a molecule. Mathematical approach would work here as well. You just have to remember, hydrogen's not going to have 8 groups around it. It's going to have just 2. So if I take 14 minus 6 minus 8, I still get 0 on the center atom. But you have to remember that the hydrogens only have 2 electrons, not 8. The only place where that mathematical approach kind of fizzles out is if there are outer atoms that break the octet rule for formal charge reasons, then you can't use that mathematical approach. The chances are pretty good if you do have something that breaks the octet rule, it's not going to be an outer atom, it will be an inner atom. there'll be a center atom. All right, question 22. The fact that boron dichloride is planar, that's not right. That should be BCl3, not BCl2. So can't fix that on here. I'll have to check that later. Boron trichloride is planar. Nitrogen trichloride is pyramidal. What is the best rationalization for that? So we're talking about BCl3 versus NCl3. This one is trigonal planar. This one is trigonal pyramidal. Why is this one planar and this one pyramidal? What's the best explanation of the ones that were given? Which one? B or D? B. B. Yeah, the main reason is that lone pair there. That lone pair, remember, lone pairs of electrons push on our molecular structures. Now, you could make an argument for D if the hybridizations were quick. BCl3 is sp2 hybridized. There are 3 groups. Those 3 groups are naturally going to orient themselves in that 2-dimensional plane in a triangular shape. sp3 hybridization is a tetrahedral shape. And so naturally, we're going to get more of a pyramidal kind of look, especially when one of those tetrahedral spots is occupied by that lone pair. So if those hybridizations were flipped, then that statement would be correct and be a really good explanation for why the difference exists in the structures. However, it's not. In fact, the whole statement is completely incorrect. And so we would remove it from consideration. Now, one other thing I want you to notice in problems like this, there are usually correct statements that are woven into the distractors here. Nitrogen is more electronegative than boron. Nitrogen is also smaller than boron. Those are true statements. But we know that molecular shape is irrelevant to those 2 particular statements. It has everything to do with the bonding around that atom, the hybridization around that atom, not so much about its electronegativity, not so much about its size. In fact, in that particular case, size really doesn't matter when it comes to molecular shape. All right, any questions with these 3 here? All right, let's look at number 24. Sulfur dioxide can be described by the structures shown. Structures shown are being these ones over here. What can we say about those 2 structures? Can we say that the bonds in sulfur dioxide are of equal length? and that the electronic distribution in the sulfur to oxygen bonds is identical. Could we say that the single bond is longer than the double bond, and that there is a difference in the structure itself? Okay, Alexander says it's C. Electron pair in the sulfur dioxide alternates back and forth, and that the two bonds appear to change positions. Double on one side, then on the other. Double on the one side, then the other. Or is it that the molecule spins? Now we actually have two different bonds, a single bond and a double bond. It just appears that they're changing places, but we're just seeing it spin in place. Which one of those four is correct? Let's do a straw poll here. Show me one of four fingers. One for A, two for B, three for C, four for D. None of you are correct. None of you are correct. One of the things that comes out on these kinds of examinations is a real knowledge of definitions. What does this double-headed arrow mean? What do we call these structures that are linked together by that double-headed arrow? Right, these are resonance structures. The whole point of resonance is showing equality between the structures that are linked together. So it's not that the electron pair is alternating between the two, it's that it's evenly distributed. Resonance structures show the equality inside of the molecule itself. So reality, there is no single bond, there is no double bond. There's a bond and a half between each. That's where our definitions have to come in. So when we're looking at the conceptual parts of this examination, one thing that we really want to make sure that we have a good handle on, this came out in the morning lecture as well, we want to make sure we have a good handle on our definitions. That when it comes to certain key terms out of each of the chapters, that we have a good handle on what those terms mean. Because if we understand what resonance is, we understand the definition of resonance, then there's only one real, true possible answer out of these four. Because other than letter D, which is just kind of silly, it basically no, you're just looking at it wrong approach. Just wait, it'll spin around again. That double bond's really on the left side, I swear. Just wait, it'll turn. Other than that one, the other three are pretty viable. They make sense in some way or another. Until we bring in the idea of resonance. Then with resonance, we go, okay, now it's A. That's the definition of resonance. All right. Number 26. We didn't talk specifically about energy in this course, but there are going to be some energy related questions on the final. And a lot of them are going to be easy stuff like this. This is asking about bonds. So here I have a compound. The question is, what are the most likely products if a molecule of this new compound were to be bombarded with high energy photons? The answer to this question is actually really simple. Which bond is going to be the one that's the most likely to be picked on? Which bond is going to be the one that is going to be the easiest to break? Because the easiest bond to break is going to be the one that gets broken. So which bond is going to be the easiest to break of the four that we are getting? C to Cl. It's the lowest energy. This bond is going to require the least energy to break. And so that's going to be the one that breaks. All the ones that are higher energy, they're going to be more difficult to break. They're not going to break, at least not initially. So if we're going to break the CCl bond, what's going to be left over? Well, Cl is going to be broken off. What's left? CF3CH and F. Thing that you have to remember is that this is an organic compound. Those carbons are going to be linked together. That's the compound. The question is, which bond gets broken? Do we break this one? Do we break this one? Do we break this one? Or do we break this one? And based off of the energies, we can see that this green bond, the carbon to chlorine bond, is the easiest one to break. Since it's the easiest one to break, that's the one that takes off. The chlorine atom is going to be left behind. And the remainder is going to be left behind as well. So energy questions like this, they seem complicated, but usually they're not that complex. Questions like this, we're talking about, you have to get to the heart of it. What is this ultimately asking? It's asking where this is going to break apart. And to that end, we always know lowest energy wins. When it comes to, does this chemical reaction occur? The answer is always going to be, well, how much energy does it take? The more energy it takes, the harder it is to do. For number 28, just as a review, what do I look for when I'm trying to find nonpolar molecules? What distinguishes a polar molecule from a nonpolar molecule? Right. Symmetry. Polar molecules don't have it. They are asymmetrical. That asymmetry in their molecular structure is what creates that division to create an electron-rich area, the negative side, and an electron-poor area, the positive side. If it's nonpolar, then it has symmetry. So of our options here, which one is symmetrical? Now, based on formula, we can eliminate two options. There is no way that a molecule with three different elements in it is going to be completely symmetrical. There is no way that an element that has one bond and the two elements on either side of the bond are different. There's no way that's going to be symmetrical either. So it comes down to water versus tetrafluoroethene. Now we could draw these, or you could just rely on your instincts here. If we haven't hammered it into your head after 16 weeks that water is a polar molecule, then Monday's probably going to go pretty bad for you anyway. So water's polar. C2F4, if you drew it out, you'd have a double bond between the carbons. There's your symmetry. This is a sp2 planar molecule. And other than the carbon-carbon bond, which has its own internal symmetry, you've got three-dimensional symmetry from the fluorines to each other in all directions. All right, number 37. Which species contains both ionic and covalent bonds? Good chance there's going to be a question like this somewhere. Kind of a classic question. Or there's going to be a close cousin of it. Which of these is only ionic? Which one of these is only covalent? That kind of thing. What am I looking for as far as the ionic character is concerned? I'm looking for ions. In particular, usually I'm looking for metals and nonmetals together. And if I'm looking at covalence, I'm usually looking at nonmetals and only nonmetals. So if I have both, then what I'm looking for are ions with covalent structures. What kind of ion has a covalent structure in it? A polyatomic ion. Something like ammonium or carbonate or acetate, where I've got all of these atoms together and I can draw their ionic form using a Lewis structure, but in the end it also is charged. And as a charged molecule, it can attract other charged molecules to make a compound. So answers like B looks really attractive, but it's missing something. There's no other ion here to make it an ionic compound. It's an ion, the hydronium ion, but that's where it stops. Covalently bonded with a charge. Excuse me. Covalently bonded with a charge, but no countercharge. Something like letter C. I've got ions, sodium, potassium, sulfide, but none of them are polyatomic. All the forces here are ionic. Letter A looks like it should be, because NH3, that's almost ammonium ion. BF3, all that's non-metallic. It's covalent, completely covalent. The one that contains both is the magnesium cyanide. I've got the magnesium and the cyanide. There's my ionic attraction. And then I've got the covalent bond inside the cyanide ion itself. The carbon and the nitrogen are covalently bonded together. So covalent inside of the cyanide, ionic in the attraction between the magnesium and the cyanide. Right. Number 38. How many sigma and pi bonds are represented in this molecule? Now, what drew you to A, Sydney? Okay. Now, the test writer kind of gave us the clue here. All 4 of those add up to 9 bonds in total. Question is the breakdown. If you notice that that is the case, where all the answers are basically the same, they're just different variants of each other, you can count one or the other and know that the other one's correct. Now, in my case, what I would do, I'd be counting pi bonds because they're easier to find. Less chance of making a mistake. I look at this and say, okay, I've got 1 pi bond in this double bond. I've got 2 pi bonds in this triple bond. 2 plus 1 is 3. And since everything has to wash out, that must mean that A is correct. Could I go another direction? Could I count all the sigmas? Yeah, I can go 1, 2, 3, 4, 5, 6. I get the correct answer there as well. What was that? Any questions out of this section? All right, let's look at something else then. Let's stay in this mode. Let's look into chapter 6 a little bit here. Phase diagrams. On the chapter 6 quiz, a lot of you missed the phase diagram question because you mislabeled the phase diagram entirely. So just as a refresher here, the solid region is this region with the low temperatures and the high pressures. The gas region is the high temperature, low pressure region. Liquid is in the middle. So if I'm looking at point F here, what is point F describing? What 2 regions is it between? It's between liquid and gas. Now remember, anything on the line itself represents an equilibrium point between those 2 phases. So both of those phases are going to be there. So the answer to the question here is B. Liquid and gas would be present at that spot. Keep in mind that this is, by all intents and purposes, a boiling point. This is a spot where the liquid can go into the gas phase if the temperature is high enough, or if the pressure suddenly were to drop. And this is, again, this comes back to another one of those definitions. What is the definition of boiling point? Remember, it's the point, the temperature where atmospheric pressure matches vapor pressure. And so, from a phase diagram standpoint, if I lower the atmospheric pressure, that's going to lower the temperature at which we need to get the boiling. That's why it always slopes down there. All right, let's do a little bit more review here. What is point B? Mason, say it again.
It's a triple point.
Yeah, it's a triple point. What happens at the triple point? What's present at the triple point? Yeah, all three phases are there at the same time, and they're all changing between each other. Right, what's point D? Okay, Micah? Yeah, it's the critical point. At temperatures and pressures above point D, then we talk about supercritical fluids. At temperatures at and below the critical point, we can still describe things as being either liquids or gases. And so long as we don't cross that threshold, we can kind of put supercritical fluids into this box right here. So long as we don't cross the threshold of the critical point, either in pressure or in temperature, we can distinguish between the two. So if we're at the critical point, if we're at the critical temperature and we raise the pressure, well, it just continues to be a liquid. If we're at the critical point and we raise the temperature, it just goes into the gas phase. But if we go both, then we start to talk about a supercritical fluid. All right, last question that we'll talk about here. And if things come up over the weekend, by all means, bring those to review session on Monday. According to this phase diagram, the second one here, what is the normal melting point of the pure substance, whatever this pure substance is? What is the normal melting point? Okay, Mason, you're correct. It is -15. We have to remember, again, this comes back to definitions. When we describe a phase change as normal, that means that the pressure has to be 1 atmosphere. So we needed to look at the 2 phase transitions at this top line here. The normal melting point would be the one that goes between the solid phase and the liquid phase. That's how we came to -15, as opposed to 140 degrees, which would be the normal boiling point. But that's where we're going to stop for today and for our review here.